Thank you very much for the invitation and for the opportunity to talk about this recent paper that I wrote on essentially generalized Landauer's principle. So as Roman was saying, so I'm more used to giving these big colloquium talks where I talk about everything a little bit, about nothing really in depth. But for this particular audience, and in particular since Ellen invited me, I thought it might be a good idea to talk about one recent project that is interesting enough and also simple enough that we can talk about the technical details. So as was said, I'm a professor at the University of Maryland, Baltimore County, and this is where the money comes from. I realized that UMBC is maybe not the most famous institution, so I always like to show this picture to give you an idea what campus looks like. So we are located right outside Baltimore. So, or more specifically, if you sit in the Inner Harbor, right downtown Baltimore, and you look towards west, towards the Appalachians, then this is what you see. This is our campus. West is back there. This is where the Appalachians are, the mountains. And the physics building is very, very easy to recognize. It's the one with the observatory here. Here's a zoom in into the physics building. And before the world went totally crazy and we all used to go to work on campus, you usually would find me here. This is the window to my office. Now, when talking about UMBC, we often get mixed up with the University of Maryland College Park. So Maryland actually has a university system of Maryland, which is very comparable to the UC system or University of California system or the University of Texas system, or what you're probably more familiar with USP, University of Sao Paulo. The only difference between USP and the University of Maryland is that we're truly independent entities, where in Maryland we have about 10 universities, of which 2 are large research universities. The biggest one is University of College Park, which is a monster with almost 50,000 students. It's about half an hour south of our campus. And we are what in the US is considered mid-size. So we have about 15,000 students. This doesn't mean that we're small in any sense, in particular in physics. We do cover the 4 core areas of physics. In particular, we have a group in quantum optics and quantum information, condensed matter physics, atmospheric physics, and astrophysics. Most of the work of mine that you may be familiar with probably falls within the scope of quantum optics and quantum information, a little bit of condensed matter physics. But we also sometimes think about cosmological objects and astrophysics. Atmospheric physics is something that I haven't really touched upon yet, but it may come at some point. Now, the main motivation for this talk is really trying to better understand the thermodynamics of these quantum technologies. And this is just a random collection of pretty pictures that you find around the web of what you have here. This was an earlier generation of Google's quantum computer. So this is not Sycamore, it's one that they had before, whatever it was called. This is a picture from the Microsoft homepage, and this is a smaller startup, Silicon Valley startup, Rigetti. Now, for this audience, I don't have to make it clear that in order to understand these technologies, we do need to understand the energy budget. If we want to optimally operate these quantum information processing devices, quantum computers, we do need to understand the thermodynamics and the optimal control of these devices, such that on the one hand, we fully understand the resources that are necessary to operate them, and on the other hand, that we understand the modes of operation that allow us to work with these technologies in a way such that the delicate nature of the quantum states are not tainted. All right, this is the outline for today's talk. Just to make sure that we're all on the same page and to clearly state what I want to do, I will talk a little bit about what people have done from Maxwell's demon all the way up to quantum computing, which means, in essence, I want to talk about Landauer's principle a little bit, what its applicability is, what its shortcomings are, and what the usual assumptions are that you make when you talk about Landauer's principle. Second part of the talk is then on this recent little preprint that I wrote. So this is the reference where we'll be aiming to derive a generalized version of Landauer's principle, which maybe is not the end of the story, but maybe gives us a very, very good starting point for how to think about quantifying energetic resources when talking about quantum computing. In particular, I want to talk about optimal gate design, and then I think what I really want to emphasize is this quantum error correction. Also, let me emphasize, this talk is really supposed to be interactive, in the sense that whenever you have a question, please do not hesitate. Ask me right away. As you see, I only have 25 slides, which should cover about 45 minutes or so, and that should give us plenty of flexibility and opportunity to discuss. So if I say something that is not clear, or if I'm losing anyone, I know that a lot of students are in the audience, please interrupt and ask right away. So this whole discussion goes back to Maxwell's demon. And Maxwell's demon is something that you've probably seen already at an undergraduate class in thermodynamics at some point. But I do want to highlight a few issues that I think are worth considering. Now, to quickly run you through the setup, which is mostly a reminder, is imagine you have the standard setup in thermodynamics, which is you have a bipartite box with slow and fast particles, cold and hot particles, so to speak. Then we have a little trapdoor, which is very, very well greased. So Maxwell originally called it a neat-fingered being, and that just means that this neat-fingered being can open a trapdoor without doing any work. Or in other words, this trapdoor is frictionless. This is what I mean by well greased. Then what this little neat-fingered being, this demotic entity, does is it measures the velocity of these particles. And whenever there's a particle with high enough speed coming from the right to the left, it opens the trapdoor such that all red particles are allowed to go to the left. And whenever a blue particle comes, which means a slow particle comes from the right to the left, the trapdoor remains closed, and vice versa, meaning if there's a blue particle coming from the left going to the right, it opens the trapdoor, but if there's a fast particle coming from the left to the right, the trapdoor remains closed. Now, in the long run, what happens is that all the red particles accumulate on the left, and all the blue particles accumulate on the right. Now, this is obviously at variance with the Clausius statement of the second law, which tells us that heat always flows from hot to cold. Because due to the sorting of the particles, what is going to happen is that effectively the hot medium is going to become hotter, and the cold medium is going to become colder. Or in other words, the average velocity, the average speed, sorry, not the average velocity, average speed in the left compartment is going up, and the average speed in the right compartment is going down. Now, you know how this works. If we want to repair the second law of thermodynamics, or rather the statements of the second law of thermodynamics, we do need to make sure that we actually quantify all resources that are consumed during the process, this overall process by all entities, which means in particular we do need to account for the information that is processed in the memory of the daemon. Or in other words, we do need to account for the physical mechanism of taking the measurement and writing a record of the measurement outcome into the daemon's memory, such that the daemon can take action upon the outcome of the measurement. Now, Maxwell's daemon was originally incepted in the 1860s, and only rather recently, just about 8 years ago, I think thermodynamics of information became a real thing, in the sense that we fully understood that information does need to be treated on the same footing as work or heat, which means if you open a standard textbook, you will always find a description of work reservoirs and heat reservoirs. And what we made very, very clear in this paper is that you also need to account for the information reservoirs. And if you want to formulate statements of the second law, you better make sure that you actually also include whatever is exchanged with the information reservoir. Information reservoir just means the daemon's memory. But obviously, for 150 years, this is not a problem that was totally ignored, but rather a lot of work had been done along the way. And the hallmark result, or that's probably the most important result in computer engineering, is Landau's principle. I will illustrate Landau's principle on the next slide with an experimental verification, but I do want to give you a little bit of a more conceptual understanding of the principle before we move on. So Landau was very much interested in understanding the thermodynamic resources that are consumed when processing information. Not so much in a resolution of Maxwell's daemon, how it's often presented, but rather he was really interested in what is the energy that I need to feed into my computer such that this computer processes information in a way that I wanted to do it. And he considered the simplest possible scenario that you can imagine, and that is simply erasing one bit of information. Erasing means that initially so let's talk about zeros and ones to make that a little bit more precise. So let's say initially the system was either in state 0 or in state 1. And then I do something to the system. What he really considered was, he says, okay, let me attach this bit to a thermal reservoir, which is what typically happens in any technology, like at the computers that we're staring right now. And then I let the system relax towards a new ground state. And during this relaxation, the system is going to deterministically, with certainty, be reset to the 0 state. Now, logically, what that means is that I have a 2-to-1 map, which means independent on whether I start in 0 or 1, I always will go to 0. So I have 2 possible inputs, but I only have 1 output, which means logically this is always an irreversible operation. However, and this is something that we've also understood a bunch of years ago, is that thermodynamically this can be made reversible, which means we can do that through quasi-static realization, or in other words, if you very slowly modulate the double wall or your two logical states, then this relaxation can really happen reversibly as a succession of equilibrium states, which means logical irreversibility and thermodynamic irreversibility is not the same. And this is actually what's really encoded in Landau's principle in the way that you've probably seen that many times before. So on the left-hand side, you see the average work that is necessary in order to erase this one bit of information. And at the right-hand side, what we always have is this KBT log 2. Now, if you squint at it a little bit, it becomes immediately clear that what you're actually looking at is just the free energy difference of a distribution that was originally 50-50 in 0 and 1 state, and then was reset to a distribution that is with certainty in the ground state in the 0 state. Which means what we're really looking at is just the maximum work theorem. Work is always larger or equal to the free energy difference for an isothermal process. And this is something to keep in mind. So Landau's principle really is a statement of thermal relaxation, but expressed in terms of this logical language, such that we can talk about the erasure of a bit. Now, how does that look in an experiment? And since 2012, there have been many other experiments, but I like this one because not only was it the first one, but it's also particularly easy to explain. Now, what they did was they took a colloidal particle in optical tweezers. So the actual experimental setup is not that important. What is more important is understanding the physics of what they did. So let's say we have two wells, left and right. So these are the measured double wells that are experienced by the colloidal particle, which is illustrated here as a red bubble. And in this particular scenario, the particle is originally located in the left state. Then what they did is they adiabatically very slowly modulated the trap. Namely, they took down the barrier, then they skewed it, then they wait for the thermal relaxation. This is exactly what I said. So you need thermal activation to go over this barrier, thermally relax into the ground state until you're on the right, and then you raise the barrier again. Now, what you immediately see is that if you do that thermodynamically irreversible, which means if you do that in finite time, then the transition probability is not going to be 1, but rather thermal fluctuations also might kick you back, which is why they looked into the success probability. And what you see here is, so they plot that here in terms of the force, which means how far do you need to tilt. And what they see is if you tilt far enough here, so if you change the angle by enough, then the success probability goes up to almost 100%, 95%. And the reason why it doesn't go up all the way is because they still need to perform the experiment in finite time. It's a real experiment, it's a colloidal particle, which means there's always going to be a small chance that even in the tilted potential, the particle is going to hop back up. Now, I assume that many of you are familiar with stochastic thermodynamics, which means you've seen these kind of plots before. So strictly speaking, since it's thermal relaxation, what we're looking at here is the heat, the work, but that's only subtlety. But what he sees is that the distribution of energy consumed during this process has a width, which has the usual exponential asymmetry that you would find in fluctuation theorems. But that's more remark for the experts. An argument that is probably clear to all of you is then the slower I modulate this trap here, the slower I go, which means the more closely I operate at the quasi-static limit, the sharper this inequality becomes. Equality is achieved exactly for a reversible process, and this is exactly what you see here. So in the dashed line, you have kBt log 2 as a function of t. You plot the total energy, total heat, total work performed during the process, and if you go very, very slow, the curve, the measured heat, asymptotically reaches kBt log 2. Okay, so why is this important? Well, for starters, it actually took more than 50 years to verify that Landauer was right, which is actually not all that obvious if you go to the original paper. In the original paper, the derivation of Landauer's principle is really a little bit, let me try to be politically correct. Today, you wouldn't be able to publish such a paper after peer review, in the sense that many of the arguments that Landauer uses are really hand-waving and plausibility arguments. They are not sound from a modern statistical physics point of view. And I think my major issue is that he simply equates the Boltzmann entropy, the entropy of whether you're in 0 or 1 from this logical operation, with the thermodynamic entropy. Now, if you look at this scenario, if you deterministically start at the left state, then you're obviously not in a state of equilibrium. If you were in thermal equilibrium, then in that case, the probability to be in left or right would have to be 50-50. You would have to allow for thermal equilibration. But that's not what typically happens. And computers do not operate in thermal equilibrium. Thermal equilibrium would be bad, very bad. Why would that be very bad? If you were in thermal equilibrium, you would have constantly transitions between your logical states, which means you never would do a real computation. You never would actually get any meaningful output. This is one of the reasons why it took so long. The other thing which I really like about this experiment is that it illustrates this argument that I was trying to make here. Landauer's principle really relies on the thermal relaxation, on the thermal activation to go from 0 to 1. Now, the other thing that Landauer's principle also doesn't capture is that it only talks about erasure. Now, in the experiment that I just presented on the previous slide, erasure shouldn't be any different from writing. And what Alec Boyd and Jim Crutchfield showed in this PRL is that indeed, if you look more carefully into information processing, it's not only the erasure that costs work, but there's actually an amount of work or heat that you have to do in the system for the modulation. So if you look into the full energy balance of what you're doing here, and there's always heat associated with the erasure and with measuring, which means writing information. Now, I spare you the mathematical details because this really goes into a deep analysis of a dynamical system where you would need a lot of arguments from, in particular, deterministic chaos to fully understand the model. The only point that I want to make here is that in their model, whatever it might be, they have a control parameter gamma, which they can play with, which tunes essentially the behavior of the system. Erasure is achieved for gamma equals 1/2, which is right here. Now, if you look at the yellow bar, what we see here is that indeed, for this particular scenario, which Landauer originally worked with, excuse me, erasure costs you exactly kBt log 2. This is what we would have expected. But as soon as we start playing with this asymmetry parameter a little bit, what he sees is that erasure doesn't always cost you. Actually, if you go somewhere here, erasure is going to cost you significantly more than kBt log 2. Here, you're even going to get energy out. Erasure becomes negative. And then writing information can either be you get energy out, or if you go to this particular value 4/5, it flips completely, which means erasing and writing information costs you energy. Again, the mathematical details of this particular model are way too specific for the purposes of this talk. However, the main message from their paper is that it's not only erasing information that is going to cost you, but also writing, which means you cannot just simply say that Landauer's principle is the only thing that you need to worry about when building a computer. But you actually need to carefully account for all resources consumed when processing information.
Excuse me, I'm trying to understand what it means, the negative energy to erase information. Does it mean that when you erase, you go back to a state of lower energy? I mean, it's
yep, that's exactly what it means. So remember, here we're looking at a scenario where a system is coupled to a heat reservoir. And depending on how you modulate, so you're doing work on the system by modulating the potential. And then the first law of thermodynamics doesn't actually tell you anything about the direction of where the heat goes. If you start in a state that was energetically higher than you are in the end, then heat has to leave the system. This is when you get energy out. If you go to a state where and there's more energy in the system than it was before, then you took heat from the environment and put it into the system.
Mm-hmm. Okay, thank you.
So, sorry, Sebastian. So this gamma parameter, it would be anything physical that you can do to the system. For instance, you're saying modulation of the potential would be somehow related to this gamma parameter, right?
In principle, yes. This is what you would like to have. Okay. The reason why I'm a little bit hesitant is, so this is really a dynamical systems analysis, so they write on a dynamical map, and I'm not entirely sure how you would translate that into something that you can do in an experiment.
I see, okay.
Yeah. Essentially, yes. So this is why I didn't write down the model, because there's no direct connection to a physical situation. Again, the main message just from this paper is we need to be careful with the energy balance. It's not true that only erasure costs you, but there are other costs that you need to be concerned with.
No, thank you.
All right. So everything that I wanted to illustrate here is, I think you're all familiar with Landauer's principle, but maybe you haven't quite picked up on the subtleties, which are, we do always need some thermal relaxation or maybe chaotic evolution. And this is essentially such that we have a notion of temperature. It's kBT log 2. And we always need to talk about this temperature. Now, what David Wolpert put into this very, very nice review paper, it's a topic review published in JPA, titled Thermodynamics of Computation, is that he basically just gives you a long list of all the other things that you need to worry about. One is, well, we actually need to worry also about writing information. It's not just erasure, and this is what I just illustrated on the previous slide. But there are also many other things. So we actually need to worry about the internal entropy of logical states. Internal entropy means, well, if you're in a double wall potential and the colloidal particle is allowed to fluctuate back and forth, then there's something like an internal energy, which means you can a local internal energy and local internal entropy, which you also can extract. Then the question is there an interplay between the entropy that is encoded in the logical states and the information varying degrees of states, which is just in the thermal fluctuations within the potential value, or is there not? But this is something that needs to be considered. And in a real computer, we are typically not only working with a single bit, but we're working with many. If we have many, we actually do need to worry about complexity, meaning is there any thermodynamic resource that is related to how the different bits interact with each other? And complexity, and this is, again, just a remark for the experts, so I really mean here algorithmic complexity, and there's been some discussion in the literature. In other words, what we just need to worry about is when applying Landauer's principle to a real computer, we cannot just take bit erasure for granted and the holy grail, but rather we need to very, very carefully think through what informational resources are consumed with information, and not only logical information in this 2-to-1 map, but any kind of informational entropy that is being processed during the computation, and any processing of entropy is going to cost thermodynamically. What I consider an even bigger issue.
Can I ask?
Unfortunately, I don't see you. So.
Okay, Professor Deffner, what do you mean by internal entropy of the logical states? Because in general, I think the logical states are pure states. So the entropy Okay. Thank you.
If we go back to this experiment, then I can assign the entropy that is carried only by the information-bearing degrees of freedom, meaning left or right. Let's say I start in a situation where I'm 50% on the left, 50% in the right. Then the entropy, Shannon entropy that I would assign to that is exactly log 2. However, this is a real physical system, which means that this colloidal particle, due to the thermal reservoir, is going to fluctuate in this potential well, right? Which means it's going to carry some local entropy, some local thermal entropy that simply comes from the thermal oscillation of the colloidal particle in this well. Now you could imagine a scenario where you directly access the entropy that is encoded here in the logical state, in the potential well, and maybe use that as a resource that you somehow can exploit in the solar erasure process. The question then is, well, does Landau's principle still hold or not? Can you somehow exploit this internal entropy? And what David Wolpert showed was, yeah, you actually can exploit that. If you extract this additional entropy, you can use that as an additional work reservoir to outperform Landau's principle. So you can actually do better if you come up with control strategies that allow you to access directly this additional encoded entropy.
Oh, okay. Thank you. I was thinking about not about Shannon entropy, but about von Neumann entropies. But for pure states, it's a little bit strange to me.
Okay, this is actually a very, very good question that I will come back to in 2 slides.
Okay.
I will make this more precise. Basically, this is really also one of the issues that we need to think about.
Oh, thank you so much.
But that's a very good question. So, but before we go there, and I want to motivate a little bit more why this is actually an issue. So about half a year ago, I went to a little conference on reversible computing. And these computer scientists working in reversible computing, and this is essentially what you were just saying, they said, well, Landau's principle is nice, but this is not something that we ever have to worry about in reversible computing. Reversible computing, without making that overly precise, is built on one-to-one maps. For those of you who are familiar with adiabatic quantum computing or with quantum annealing, this is exactly what you do. You start in a ground state of a Hamiltonian, you have some adiabatic manipulation, you start in another ground state, so you start in a specific initial pure state, you go to a specific final pure state, that's a one-to-one map. The von Neumann entropy, or the entropy, so to speak, has changed. That doesn't sound right, because it seems like if I build reversible computers or quantum computers, all of a sudden I can do computations for free. So typically there's no free lunch. Whenever, at least whenever I hear that something is completely for free and there are no thermodynamic resources consumed, I have the feeling that something must be very wrong and I get very suspicious of it. The other thing that I have is, issue that I have is everything that I've shown you so far is based on classical stochastic thermodynamics. And unfortunately, I don't know who asked the question, but whoever just asked the question was already talking about the von Neumann entropy, which means we have to talk about quantum systems, which means if we're talking about quantum systems, we need to be very, very careful with what we actually call work or how we compute energetic resources. Okay, but before we jump at the new problem, let me just quickly do a little bit of bookkeeping. So what we do have is Landau's principle as the foundation of modern computer science. So if you talk to a computer scientist, if they know nothing about physics, if they've never heard thermodynamics, they do know Landau's principle. Landau's principle is the foundation for accessing and assessing any energetic cost of information processing. So this is universally accepted. And if you would like to have this, and I think you agree with me on that, is, well, we would like to have a Landau's principle that actually tells us anything interesting about quantum computing, because it's wrong. But at the same time, we also need a very clean framework. So we don't want to couple our quantum computer to a thermal reservoir in order to assess very, very delicate and attach, or would inevitably lead to decoherence. classical arguments. So we want to be sounding clean. So information that has been processed in a unitary quantum operation. And we need to do that in a way that thermodynamic considerations pop out naturally, which means we do not want to start with a framework where the thermodynamics is already built in, but rather we want to start with a very, very clean question, then do a little bit of math, and then in the end come up with an answer that is thermodynamically consistent. The reason why I'm saying that is because there are a lot of papers out there where people start with exactly the opposite motivation. So they start with a clear thermodynamic statement, and then they somehow try to develop a model that fits the bill, such that you get the thermodynamics in the back, which is maybe not necessarily what we want to do, because what we really want to do is we want to formulate, again, something that is universal and actually applies in a way would be happy with it, and they don't understand thermodynamics. It's just a random list of a couple of papers that I read and that I liked and that somewhat shaped my thinking. Now, what you find is that
so the connection is not so.
Yes.
Yeah, I was okay.
A lot of generalizations of Landau's principal papers start with
We cannot
Yeah,
can you hear me?
we can,
Yeah.
connection is very bad.
Yeah, there are a bit of slowdowns.
Yes.
I think it's on your side because we. Okay.
On my side?
Maybe Sebastian, if you
that's
turn
not
off
good.
your video, maybe that
Yes,
will.
it's a good suggestion.
Sure. Leave call, turn off. Okay, is that better?
Okay, perfect.
Can you hear me
Yes.
better now?
Yeah, maybe
Yes.
if you could go back to the previous slide just a bit.
Can you see yourself?
Just
Yes.
to summarize very quickly,
Yeah.
because everybody was kind of asking if
Great.
it was our connection, our side, or yours. Thank you.
Thanks.
Okay. So maybe let me just go through the slide again. So what I was saying is a brief summary. So Landau's principle is a universally accepted and experimentally verified statement of the second law. All computer scientists, even if they've never heard anything about thermodynamics, they do know Landau's vision for thermodynamics of information. But what we really want is we want a Landau's principle.
Same problem.
In particular, we want a vision, classical stochastic thermodynamics.
Connection problem.
Same problem?
Yes. Sorry.
Same.
Yeah, same
Same
problem,
problem.
unfortunately. Yeah.
Everything looks still fine. I don't know what's going on.
Homa, do you think that disconnecting and reconnecting is
Yes,
a good
we
idea?
can, Sebastian, if you want.
No problem. You cannot hear me.
Disconnect.
That's what he said.
No,
Okay.
it's breaking a lot, so sometimes your speech speeds up, and it's kind of weird. Yeah.
That's not good. So you want me to get out of the call and then come back in?
Yeah, sometimes it helps.
Okay, let me do that.
Eu tava pensando que era a minha internet aqui, eu falei.
Eu também, eu demorei para falar com o
Não vou
Romão.
perder o seminário.
Eu acho que ficou todo mundo assim, né?
Olha, quem me reclama de internet aqui podia não ser Estados Unidos.
Romã ama muito o Brasil.
Also, Marcelo, your video is moving very slow. That means the connection is not good. Also,
So which video? I didn't
no,
hear it.
Professor Roman is
Yes.
also is not clear. His photo is not clear. That means there is some breaking, maybe due to internet connection not well. I don't know, maybe speed. Yeah, yes.
Yeah, it can be.
See, maybe it is from our side. I don't know.
No,
Yeah.
if yeah, I don't know. Yeah.
Hello again, Sebastian. So I think you can try again to full screen.
You are muted.
Internet with the alien is good.
Okay, so let's try this again. Okay, so how's the connection? Can you hear me?
Yeah, now it seems
Yes, we
Okay.
get your screen as your presentation.
No, it's okay.
All right. So, quick summary of this slide. So everything that I was saying is, so we have Landau's principle. It's great. But now we want to do that right for quantum systems and quantum computing, and in particular, make sure that whatever we do is clean and free of any classical arguments and thermal relaxation processes. All right. Now, as I was saying, I'm certainly not the first one to think about the problem. However, the large majority of papers out there, and this is just a small selection of them, consider scenarios where you start with an open quantum system, which means you take a qubit or something like that, attach that to a thermal reservoir, describe that with some kind of master equation, and then rederive Landau's principle. And this is exactly what I don't want to do. So I don't want to use thermal relaxation. There are a couple of other papers where people look directly into the energetics of quantum operations. This is already a little bit older. But you see, these are really recent problems from 2020. And what we find here also is that you always need some notion of temperature, which is something that Gabriel, who's in Sao Paulo, realized. And what they did was they used a completely stochastic thermodynamics approach and then took the systematic limit of t to 0 and see what you get in that case. But what I'm aiming to do is I really want to get away from this notion of temperature. Especially in reversible computing, I do not want to have to worry about a thermal reservoir in order to do my computation, but rather I really want to talk about the problem at the level of only energetic costs. All right, so when we're talking about a quantum computation, what is it that actually really happens? What is it that we really need to worry about? How do we even quantify information? And in my cartoonish sketch, we have some entity, let's call her Alice, who prepares some quantum state, your quantum state, whatever that might be, and feeds this quantum state into a quantum network. Quantum network means just some computer doing something. Then in this black box, or in this case purple box, we have some unity operations doing something, flipping bits around, doing C0s, all the nice things, and then in the end produces some quantum state. However, at the readout, another entity, Bob, doesn't actually do a full state tomography. That would be way too complicated and way too expensive. But rather, Bob takes a measurement in the logical basis, which means we have something like, excuse me, we have something like an alphabet. We have zeros and ones, and Bob just measures how often are you in 0 and 1. And if, for example, you played a little bit with IBM's Q experience, you don't really care about the correlations between the different qubits. You're only interested in how likely it is to find a qubit in state 0 or 1. Keep that in mind. That's important. You take a measurement. You don't actually care about the entropy that is carried by the pure state, which is anyway 0. But rather what you're interested in is the histogram of observing zeros and ones. Now, let's do an example to get that very, very clean in our minds. So let's think about qubit reset, which is probably the problem that is the closest to classical erasure that we can imagine. Let's say Alice prepares an even superposition of logical states 0 and 1. Then we apply a Hadamard gate, which is the quantum equivalent of an erasure, which means the Hadamard gate resets this even superposition deterministically to state 0. So this is what the Hadamard gate looks like. And you can easily convince yourself, if you let this Hadamard gate loose on this even superposition, you just get the 0 state. Now, whoever asked about the phenomenon entropy earlier, well, we start with a pure state, we end with a pure state, nothing has happened. 0 entropy here, 0 entropy there. But wait a second. The argument that I was trying to make on this slide is that it doesn't actually matter what the entropy of the overall state is, but rather what we're interested in is the likelihood of observing states 0 and 1. Which means what we're interested in is in the Shannon information of the marginal, or rather the Shannon information of the logical basis, which quantifies the amount of information encoded in the probability of observing 0 and 1. So in the ingoing state, it's with 50% probability you observe the state to be in state 0, and with 50% probability you observe the state to be in state 1. In the outgoing state, you observe the system to be with 100% probability in state 0, which means the corresponding Shannon information for the logical states has changed by log 2. Minus log 2, doesn't really matter. I'm only interested in the magnitude. So it changes by log 2. Which means the Shannon information over the logical states, over the computational states, does change, whereas the phenomenon entropy does not change. Now, what I want to do is I want to quantify the energetic resources that are consumed during this reset. Which means what I want to do is I want to estimate the energetic resources that are necessary to process this amount of log 2. All right, see how we do that. And this is why I started talking to Alan, because he gave me the answer. Until I read his paper, I had no idea what to do. The problem is, typically in quantum computing, in particular in a circuit model, everything is formulated at this level. You have unitary gates. For these unitary gates, you don't have any natural notion of energy. If you don't have any natural notion of energy, you don't know how to do thermodynamics. But what we do want is well, we want to compute things like internal energies, heat, and work. Now, what Alan showed us is that whenever you have a unitary operation, you can actually reverse engineer the time-dependent Hamiltonian such that the unitary operation that you're interested in becomes the time-ordered evolution operator under this time-dependent Hamiltonian. Now, this, as you might imagine, becomes mathematically a little bit involved, but for the simple Hadamard gate that I had on the previous slide, you can write that quite simply. So it just becomes a superposition of sigma x, Pauli x, and Pauli z, with some prefactor, where this prefactor is an arbitrary function or the derivative of an arbitrary function, which fulfills certain boundary conditions. Where you see the boundary conditions really just comes about from integrating the Hamiltonian here and then matching it with the Hadamard gate. Also, if you squint at that, so what you actually see here is this is just a magnetic Hamiltonian. So you have a magnetic field which points only in x and z direction, where a phi dot is the intensity of the magnetic field. So this is great. So what is in this paper is that it's actually a little bit more general. So this is just an example for the Hadamard gate. What Alan showed in this paper is that independent on what you want to do, if you give me, or if you give him the unitary, he can construct the Hamiltonian such that you get the unitary out that you're interested in. Which means for my purposes, I don't even have to worry about the specific unitary. I can work directly at the level of the time-dependent Schrödinger equation. So let me do that. So let me consider an arbitrary time-dependent Schrödinger equation, which is of the usual form. Now, at this point, I like to apologize because I'm going to do something that I don't typically do. So typically, I don't show any derivations or mathematical details in talks because I personally always find that a little bit off-putting, and the math usually distracts more than it helps. However, in this particular case, the derivation is so simple and so straightforward, literally only take 3 lines, that I decided to give you at least a rough sketch of how that works so that you get an idea. So what I'm interested in is I want to bound the rate of the Shannon information, or the change of the Shannon information that I had on the previous slide. Now, how do I do that? By just using the triangle inequality, I can write that in terms of time integral over the magnitude of the rate, which, by just plugging in the definition, looks like this. So the reason why I want to highlight this is because what you immediately see is it all boils down to estimating the change of the p and dots. So if I know how the occupation probabilities change, and this also ties nicely into the question that someone asked earlier. So the phenomenon entropy doesn't matter, but the probability to observe the logical state zeros and ones, that's what changes. So if I can estimate the change of these occupation probabilities, the probabilities to observe logical state 0 and 1, in terms of some energetic quantity, then I get exactly what I want. Now, with an almost trivial argument, you can show very, very quickly, by just employing the Schrödinger equation, that the change of the occupation probabilities can be estimated by this. And if you've ever seen any of these derivations, for example, in shortcuts to adiabaticity or quantum speed limits, you know what you do. You use something like Cauchy-Schwarz inequality to separate the trace of the product of these two operators, and then you're done. What I like to use is as a generalization of the Cauchy-Schwarz inequality, which is called Hölder inequality, which is exactly what we have here. And if P and Q are chosen to be 2, then you just get exactly the Cauchy-Schwarz inequality. But this is a little bit more general. So if I choose A to be the Hamiltonian and B the rest, then what I end up with is that the change of the occupation probability is upper bounded by that thing, which I can plug into what I had here before. Now, what I like is I get the norm of the Hamiltonian, and I will say more about this. This is already very promising, but it's still an ugly convolution with something that I don't really know how to interpret. However, at this point, I don't really care about a tight or precise estimate. Right now, I just care about some estimate that I can discuss, which means I might as well just estimate whatever the thing is by its maximal value. And if you do that, then what you find is writing now the Shannon information in bits, simply because it looks a little bit nicer. The change of the Shannon information is given by some prefactors, which only depend on the dimension of the Hilbert space. If it's cubist, that's just 2. It becomes very, very simple, times the time averaged norm of the Hamiltonian. Time averaged norm of the Hamiltonian. So for those of you who have read literature on shortcuts to adiabaticity or in quantum control, you will, should get very, very excited, because this is exactly the cost functional that has been discussed for about 5 years now in the literature, and then assessing the energetic cost of any control protocol on a quantum system. And as I was saying, I wasn't aiming for this particular result, it just dropped out. So what we have here is that if I want to quantify the energetic cost of a gate operation, then up to some prefactors that only depend on the specifics of the Hilbert space, the cost is determined by what has been well established as the cost of quantum control. This is very, very nice and promising. Just a quick side remark. So if you estimate this thing here by the maximum, you either do that by for a d-dimensional Hilbert space, finite dimensional Hilbert space in terms of this. But if you want to do that for infinite dimensions, things become a little bit more tricky. But as long as the energy of the Hilbert space is bounded, you still can do something similar. But the main takeaway message is that if I want to assess and quantify the cost of a Hamiltonian gate operation, then everything that I have to look at is this time averaged norm of the Hamiltonian. And let's illustrate that again for qubit reset. If you just compute all of this for qubit reset, what you end up with is that the cost for qubit reset is literally just given by the time averaged magnitude of the intensity of the magnetic field, which you immediately recognize as power input into the system. Now, there are all kinds of interesting questions that you can ask us. So once you have something like this, you can ask, for instance, can you optimize? Is there a way to get close to this bound here? Or how bad are we doing, given that I use triangle inequalities, Hölder inequalities, none of these are particularly sharp. And to quickly convince myself that I'm not going completely insane and that everything is still sound, I again looked into Alan's paper, and he suggested that the simplest way to implement the Hadamard gate is with a linear protocol. And I simply asked the question, is this linear protocol actually optimal, or can I do better? How do I do that? So let me take the linear protocol and add some Fourier modes. And in the simplest case that we only have one Fourier mode, you get the plot over here, where the cost, which is here the right-hand side, is given in blue. And in left, you just get the change in Shannon information, which in bits is just 1. What we see is this, well, there's a factor of 5, 4.5 or so between the cost and 1. That's maybe not so nice, but at the same time, it's also not so bad. So we're not an order of magnitude away, but we're only a factor of 4. And what we also see is that for, and this is the strength of the value A for a single Fourier mode, that the linear protocol that Alan suggested is actually the optimal protocol for qubit reset. All right, so what do we have? So we have a generalized Landau's principle for reversible unitary computing. At no point did I need anything from thermal relaxation or classical stochastic thermodynamics, any of that. And rather than aiming for it, but which means simply by going through the mathematical details without having to worry about what I will get in the end, the energetic cost that dropped out is something that is very, very well established in quantum control. So it gives a nice, consistent picture. The problem that I still have, well, we would like to have some meaningful applications to real problems. I can keep playing with this linear protocols and qubit reset, but what is it good for if I can't actually say anything about reality? And I think what we theorists always should do is we always should strive to derive results that give us physical insight that we would not have had otherwise. So we want to learn something new that we didn't know before. Now, there are a couple of different directions in which we can go. So we could do full optimal control theory and design optimal gates now and look into the energetic costs of these optimal gates. Or, and I just want to give you 2 rough ideas. First one is going to be very, very brief. Second one is a little bit more elaborate. I want to make contact to potential experimental implementations. And I want to say a couple of words about quantum error correction. So let's talk very, very briefly about experimental settings. So you know that the race for the optimal fault-tolerant qubit is still open. And there are many possible platforms ranging from photonic systems or ion traps to, well, whether or not topological edge states are not going to do something or not is not entirely clear, or solid state, which means Cooper pair boxes. Now, currently for technological applications, it seems that solid state has an edge simply because it's a lot cheaper and a lot easier to manufacture than things like ion traps or photonic systems. But the problem is that these solid state systems are particularly prone to noise, simply because things that are located on a chip are strongly coupled to the rest of the universe, which means you really have to worry about dissipation and decoherence. Which means even more so than in other systems, for these solid state systems, you want to make sure that the intensity of the control fields is as small as possible. Now, what do these Hamiltonians look like? So independent of whether it's transform charge or flux qubit, one way or the other, they all built on these Cooper pair boxes. And this is just the typical Hamiltonian for Cooper pair box. It's just a squid. Superconductor Cooper, where you have the charge energy here and the Josephson energy. Here you see it's sigma x, sigma z. So it looks very much like the Hadamard gate already. Everything that I'm saying here is that now this new bound can be used to find the control protocols that allow you to do whatever you want to do with a minimal magnetic intensity. To a certain degree, this is something that you would have expected, but it's nice that this gives you a clear, consistent picture by also giving you a lower bound on the minimally necessary magnetic intensity to do the gate operation that you're interested in. But as I said, this is just a small teaser of something that might be interesting in the future. What I find much more interesting is the problem of error correction. And before we jump into quantum error correction, let's do that classically. So classical error correction, by and large, relies on repetition codes, which means if you want to reliably communicate information, you just do the same thing many, many, many times independently. And this is essentially what you do in everyday communication. If you want to make sure that you're understood, you just say the same thing again and again and again. Then the outcome, the correct outcome, is determined from majority votes. So if you do it 3 times you get 0, then you get. If you get twice 0 and once 1, you still take 0, and so on and so forth. Now let's imagine that we want to reliably erase one bit of classical information. If we want to reliably erase one bit of information, and the repetition code is n-fold, which means we have to do the same operation n times, then the thermodynamic cost to reliably erase one bit of information is simply given by n times the cost of erasing a single bit. Which means Landau's principle tells you that reliably erasing a bit is given by the thermodynamic cost of reliably erasing one bit of information is given by n times kBt log 2. Now, the question that you should ask at this point is, does this linear scaling still hold for quantum error correction? Now, think about that for a second. Keep in mind, in quantum error correction, we actually exploit genuine quantum effects, quantum correlations, entanglement, coherence. Does the linear scaling still carry over? Well, let's see how that works. Let's do that for the arguably most famous quantum error correcting code that exists, for Shor's code. Shor's code is, it looks like this. Physical qubit is in physical 0 is encoded in this state. Physical 1 is encoded in this state here. What he immediately sees is that a single physical qubit is encoded in 9 non-interacting and independently controlled qubits. Non-interacting, independently controlled. Now, the norm of a Hamiltonian of non-interacting qubits is just the direct sum of these 9 terms, which means the norm, the trace operator norm, the norm of the Hamiltonian simply becomes the norm of 9 identical and independent Hamiltonians. The norm is for non-interacting Hamiltonians is linear, which means yes. What we learned from my new bound is that at this level, the energetic cost of implementing short codes is exactly 9 times as expensive as a single qubit operation. Okay, now this is the most famous code. Question is, are there any other quantum error correcting codes that are defined what they call the perfect quantum error correcting code, which also protects against any arbitrary errors? And in this case, up to normalization, 0 is encoded in this, and 1 is encoded in this. Well, they admit in this paper that the physical interpretation of this code is far from trivial, or in other words, I'm not even sure how they came up with this. But what you see here is that you only need 5 qubits instead of 9. Also in this code, the physical qubits are non-interacting and controlled independently. Trace norm is still linear of non-interacting qubits, which means in this perfect code, you only pay 5 times the energetic cost that you would have paid for a single qubit operation. Which means this code is not only optimal in a computational sense, that you need a minimal number of qubits, but it's also optimal in the sense that you can imagine. Now, problem is, most quantum error correcting codes are not that simple. Rather, quantum error correcting codes that people are now implementing or interested in have additional energy penalties. Additional energy penalties obviously contribute to the norm. They do something to the norm. You have additional interaction terms. And examples are, for example, topological algorithms with toric codes or quantum error correction on quantum annealers, which was in this very nice paper by Daniel Lidar. Now, at this level of the analysis, and I'm also getting to the end of my talk, the only thing that I can say is it would be really interesting to now go through all of these quantum error correcting codes and rank them energetically. Because once you have energy penalties, it's not so clear anymore which of these codes are less expensive and which are more expensive. And I think this is something that I want to leave for discussion and maybe also for future work, which means just going through these different quantum error correcting codes and carefully assessing their thermodynamics. So this brings me to the end of my talk. I hope I didn't swamp you totally with too many technical details. And if you forget everything that I said today, that's fine, as long as you keep 3 things in mind. So if you remember tomorrow that I spoke about a generalized Landau's principle that is applicable to unitary quantum computing, I will be very happy. If you then even also remember that I introduced a cost for gate operations, which is not only analogous, but actually identical to what people have discussed in quantum control I will be super happy. And then a potential application of all of this is that we can look into quantum error correcting codes and better understand their thermodynamics. And that's the team from October 2019, before the world went totally insane. Thank you.
Okay, thank you very much for the very nice presentation. So, are there some questions?
I have one question. In your some previous slides, you mentioned that we can use reservoir to erase or reset the qubit.
You mean quantically, something like this here, right?
Yeah, yes. The point is, for example, we can use some reservoir or external coupling with some environment to reset the qubits, for example, or erase it. And my question is that some study about this cost to couple the system to a reservoir to reset the qubit? Because it seems to me that this work could be extended to open systems approach. For example, you can do reverse engineering of reservoir, for example.
Right. So you definitely can do that. And I thought about that for a little bit, but the reason why I decided against talking about open systems is the following. You want to make sure that the reservoir that you engineer does not introduce any decoherence that you then would have to find on top of controlling the system. So what you could do is you could try to reverse engineer an environment such that the logical states live exclusively in so-called decoherence-free subspaces. Decoherence-free subspaces are such subspaces which are protected against decoherence under open system dynamics, which would be very interesting, but technically probably also far from trivial. At this level, I didn't want to, just to say it again, so at this level, I didn't want to worry about the environment because I wanted to avoid having to think about decoherence.
Oh, okay. Yeah, because I was thinking about some extension of your results for open systems. How can we measure the energy cost to simulate some reservoir, for example? It would be interesting also. Because
yeah, that would be very, very interesting. It would be highly non-trivial. It would be a really hard problem, but very interesting.
Okay, so maybe we can talk about it later.
We definitely should.
Thank you so much.
Okay. Are there other questions?
So regarding the scaling, so you had a linear scaling when you had a classical system. So do you have any intuition do you expect a general result for the quantum version?
So as long as you have independent non-interacting qubits, the linear scaling is going to carry over. As soon as you have energy penalties and interacting terms, no idea.
I see.